So today's video is on molar mass, and I know we spent last time talking about molar relationships explained in a balanced equation, but this takes it one step further and talks about the idea of how much mass does a mole of atoms have. So if you remember this sexy looking man, his name is Amedeo Avogadro, and he is the one who we say is responsible for the idea that in a mole of anything, there are 6.022 times 10 to the 23 of that thing. That's why it's called Avogadro's number. So we give this number to Avogadro, but the truth of the matter is Avogadro actually didn't discover the number himself. Avogadro lived a long time ago, and he was actually only able to work with gases. So what he was able to figure out was that any gas, no matter what kind of gas you have, if you have that gas at the same temperature and pressure, and you have a different gas also at the same temperature and pressure, both of those samples of gases will have the same number of molecules. So Avogadro's relationship was actually about how many molecules are in a gas, and this is what it says. So now you're saying, where did Avogadro's number actually come from? And why is it given to Avogadro? Well, we'll look a little more into Avogadro later when we talk about the volume-molar relationship, but molar mass comes from someone else, and it starts with a guy named Robert Millikan. So this is Robert Millikan, and in 1909, he did an experiment called the oil drop experiment. It's a really complicated experiment. I don't expect you to know it, but from the oil drop experiment, Millikan was actually able to figure out the electrical charge on a single electron, and it's a unit called a coulomb. Once again, it's something I don't expect you to know, but he was able to quantify this charge. What's cool is, because he knows the charge on one electron, if he measures the charge of a sample of atoms and he can figure out how many electrons were in that charge, and therefore he can be able to figure out exactly how many atoms were in the sample. So Robert Millikan was able to show us how many atoms are in a sample simply by measuring the charge on the electrons in the sample. So now you're probably wondering, okay, well, what does this have to do with the mass of an atom and everything else? Well, we're going to take it one step further, and the place we're going to take it to is we're going to take it to the periodic table. So this is the periodic table. You're very familiar with it at this point. But I need you to think back to earlier in the year when we talked about how this number on the periodic table that's right up here, not the atomic number, but this mass number, is something that's known as average atomic mass of the elements. And remember, we said that if you were to take all the atoms in the world and you were to find their mass, remember, to find mass, you had protons and neutrons. But if you were to take all the atoms in the world of that element and find the mass, there's different isotopes. And so by measuring the percentage of each isotope and figuring out the abundance of each isotope, you can figure out on average what an atom of an element is going to have a mass of. And that's what this number is on the periodic table. What we were able to do, though, with Millikan's discovery was we were able to say, what if this number isn't actually the number in AMU, or atomic mass units, but this number for mass is a mass in grams? How many atoms would it take to have that AMU mass of one atom be the mass of that sample in grams? Well, it turns out that using the information from Millikan's oil drop experiment, that in order for this number right here that I'm highlighting in yellow, which is the mass in AMU, the average atomic mass of the element, to be the mass in grams, that number actually takes 6.022 times 10 to the 23 atoms. Therefore, a mole of an element has a mass in grams that is equal to the average atomic mass of one atom of that element. So let me write that out for you. So let's say it again to be clear. 1 mole of any element has a mass in grams equal to the average atomic mass in AMU of one atom of that element. So let's get our periodic table out and see what this means. This means that if I have 1 mole of oxygen, it has a mass of 15.999, sorry, there's 3 nines, 4 grams. Or if I have 1 mole of hydrogen, it has a mass of 1.00794 grams. If I have 1 atom of oxygen, it's going to have an average mass of 15.9994 atomic mass units. That's protons plus neutrons. And if I have 1 atom of hydrogen, it's going to have a mass of 1.00794 atomic mass units. So the mole connects the mass of the element in AMU to the mass of that element in grams. So let's practice with molar mass, and you're going to need a periodic table to do this, and that's fine. You may want to pull it out. I always just Google Virginia SOL periodic table to have it in front of me. So the question is, what's the mass of 1 mole of chlorine atoms? Very simply, I go to the periodic table. I see the mass of chlorine is 35.453. So I know the mass is 35.453 grams. So if I have 1 mole of chlorine, I have 35.453 grams. Same thing with strontium. What's the mass of 1 mole of strontium? I go to the periodic table. I see the mass is 87.82, which means that if I have 1 mole of strontium, I have, or is it 6.2? Sorry, it's 6.2. I have 87.62 grams. Periodic table was small when I was looking it up. But that's all you have to do. So if you have a mole of an element, you have the average atomic mass of that element in grams. So you're saying, okay, this is pretty easy. The problem is, in chemistry, we don't always have just 1 mole of a substance. Sometimes we have more than a mole, sometimes we have less than a mole. So we have to use conversion factors. And remember that a conversion factor is the fraction that is really equal to the same thing on the top and the bottom. So we have 2 conversion factors, one to go from grams to moles, and the other to go from moles to grams. And let me show you what they are. So if you're going from grams to moles, remember grams is what you're going to get rid of. So grams goes on the bottom and moles goes on the top. And remember, we always have 1 mole of element X is going to be Z grams of element X. If I'm going the other way, I'm going to do it where I want to go from moles to grams. So moles is on the bottom and grams is on top. If I have 1 mole of element X, I have Z grams of element X. So it's just a flipped conversion factor. How I do this in real life, let's look at a real element. We'll use boron as our real example. If I want to go from grams to moles of boron, this is the conversion factor. I want to get rid of grams of boron, it goes on the bottom. I want to change it to moles of boron, it goes on top. So it's 1 mole of boron, and the molar mass of boron is 10.811 grams. Likewise, if I want to go from moles to grams, I've got moles of boron on the bottom, grams of boron on top, and it's the same exact thing. I'm just filling in the numbers now. Like we always do, we put the units first and the numbers last. So now that we have our conversion factors, let's look at a couple problems involving molar mass. So here are 2 problems. We'll take this one at a time. The first is, what is the mass of 7.11 moles of copper? So remember, we do stoichiometry. We take our starting value. We have 7.11, and don't forget to write the units, moles of copper. And then we just multiply by our conversion factor. In this case, I want to get rid of moles because I have moles here. So moles of copper is on the bottom. I want to change it to mass of copper, so grams of copper is going on top. And then I just go to my periodic table. I know that if I have 1 mole of copper, I am going to have 0.546 grams. And then I can multiply it out. Once I put it in my calculator, it gives me 451.81206 grams, which is a lot. So we go back here, we see that this number has 3 sig fig. So we're going to round this to 3 sig fig, and our answer is simply 452 grams of copper. You can assume that our conversion factor has infinite sig fig. Okay, and that's always the case with the periodic table. So let's look at the second one. The second one is a very similar problem, but we're going in the other direction. So this time I have 45.32 grams of zinc. Notice that I am making sure that I write my units of everything, because the units will save you here. So I do my conversion factor, I do my units first. Grams of zinc is what I'm getting rid of. I want to know how many moles I have, so I want to change it to moles of zinc. Then I go to my periodic table, and I see that zinc has a mass of 65.39 grams for every 1 mole. And so this just becomes 45.32 divided by 65.39. So I put it into my calculator, and once I do that, I'm left with 0.6931 moles of zinc, 4 sig fig, because there's 4 sig fig over here. And this should be the same. I rounded it. It actually comes out to 0.69307.234, but rounded to 4 sig fig to make sure it's the same. And that's it for molar mass problems. So far we've looked at the molar mass of just very simple atoms or elements from the periodic table. But in chemistry, we actually have to deal with the molar mass of molecules. And molar mass of molecules is actually relatively simple as long as you remember the molar mass of individual atoms. So let's take a look at a problem. So in this case, we want to know the molar mass of the ionic compound calcium phosphate. In order to figure this out, you actually have to figure out how many of each type of atom you have in the compound. So let's take a look at this compound one by one. There are 3 elements in this compound. There's calcium, there is phosphorus, and there is oxygen. Let's start with calcium. In this compound, I have 3 atoms of calcium because there's a 3 right there. Okay? I also have 2 atoms of phosphorus. Why do I have 2 atoms of phosphorus? Well, there's a 2 outside of PO4. So each PO4 has 1 atom of phosphorus, but if I have 2 phosphate ions, or 2 PO4s, I have 2 atoms of phosphorus. And oxygen I have 8 atoms because I have 2 phosphate ions, but within each phosphate ion, there are 4 atoms of oxygen. So therefore, this compound in one molecule contains 3 atoms of calcium, 2 atoms of phosphorus, and 8 atoms of oxygen. Then I need to know that if I have not one molecule, but instead I have a mole of molecules, that means I will have 3 moles of calcium atoms, 2 moles of phosphorus atoms, and 8 moles of oxygen atoms. So I have to do a little bit of multiplication. And it looks something like this. For calcium, it equals 3, and I go to the periodic table, I find the mass of calcium, and it's 40.078 grams. 3 times 40.078 grams is 120.234 grams. Then I go to phosphorus, and I know that I have 2 phosphorus atoms. If I go to the periodic table, I know that if I have 2 moles of phosphorus atoms, it's going to be 30.973761 grams. When I multiply it out, I get 61.947522 grams. And for oxygen, it's 8 times 15.9994 grams. When I multiply that out, I get 127.9952 grams. Now that I have all of these 3, what I'm going to end up doing is I'm going to end up adding them all together. When I add them all together, I'm going to get 310.177 grams. Why did I round to 310.177 when I did all this? Because when I add them together, this goes to 3 decimal places, this goes to 6, and this goes to 4. This is my worst sig fig, so this goes to 3 decimal places right here. It is really, really important that you do all of the math first and then round at the end for sig fig. I will tell you right now, I'm not going to be a super stickler on your sig fig in your molar mass. Just get the molar mass right. That's all I really care about. So a couple practice problems here. First one says, what's the molar mass of lithium oxide, Li2O? So in this case, we have 2 times lithium, which is equal to 2 times, I believe it is 6.941. And we have 1 times oxygen, which is 1 times 15.9994. So I do the math for lithium, and it's equal to 13.882. oxygen is easy. It's 15.9994. And then I just add these two together. And when I add these two together, I get a total of 29.881 grams. So let's do the second one. What's the molar mass of zinc 2 nitrate? In this case, I have 1 zinc, so that's equal to 1 times 65.39, so we know that that's going to be 65.39 grams. I have 2 nitrogens, so it's 2 times 14.007, or sorry, 0067. This periodic table goes a little bit deeper. So I go 14.0067 times 2, and that is 28.0134 grams. And then there's 6 oxygens. 6 times O is 6 times 15.9994. And I multiply that by 6, and I get 95.9964 grams. And then all I do is I add these 3 together, so 95.9964 plus 28.0134 plus 65.39, going to 2 decimal places gives me 189.40 grams. So not a super difficult thing to do to find the molar mass of molecules. But now we're going to put it all together, and this is where it may get a little bit complicated. So here's the first practice problem, and it says, what is the mass of 3.72 moles of magnesium fluoride? Well, I'm going to set it up. I'm going to set it up very simply. We know that 3.72 moles of magnesium fluoride, and I want mass, so I'm going to write MgF2 there, and I want mass, so I'm going to get rid of moles of magnesium fluoride, and I'm going to change it to grams of magnesium fluoride. The problem is I don't know what the molar mass of magnesium fluoride is, so I've got to figure it out. So in this compound, I have 1 magnesium, and that's going to be equal to 24.305. And I have 2 fluorines, which is 2 times 18.998403, which is going to end up being equal to, it's equal to 37.996806. And when I add these 2 together, I get a molar mass equal to 62.302. So then I go and put this back into my equation. I say there's 62.302 grams of magnesium fluoride in 1 mole. I multiply that by 3.72. And when I come out, I know I need 3 sig fig. My answer is actually equal to 232 grams of magnesium fluoride. And that's how I do it. Let's try one more. So this one says, if I have 126.60 grams of iron 3 sulfate, how many moles of iron 3 sulfate do I have? Personally, I like to actually solve for molar mass first. So what I'm going to do is I'm going to say I have in this compound, I have 2 irons. So 2 times Fe, is 2 times 55.847. I have 3 sulfurs, which is 3 times 32.06. And I have 12 oxygens, which is 12 times 15.9994. You will get very used to writing some of these common ones. 15.9994 is a very common one. So 15.9994 times 12 is equal to 191.9928. 3 times 32.06 is equal to 96.18. And 2 times 55.847 is equal to 111.694. And then when I add all these together, so we're going to add them all up, 96.18 plus 111.694 plus 191.9928 to 2 decimal places is 399.87 grams. So then I can solve the problem now that I have the molar mass of iron 3 sulfate. I'm going to start, I'm going to do it down here. We're going to start with 126.60 grams of Fe2SO43. I know it seems cumbersome, but it really helps you to write the whole thing out. I'm going to draw the line. I'm getting rid of grams of Fe2SO43. I'm going to change it to moles of Fe2SO43. And I know that 1 mole is 399.87 grams. When I solve it, and I'm going to put the answer down below right here. When I solve it, I get 126.60 divided by 399.87. This is going to go to 5 sig fig because there's 5 sig fig right here. My answer is equal to 0.31660 moles of Fe2SO43. And that is how you do it. So I'm going to end today with a challenge. And this challenge problem is one that you'll be able and expected to figure out later. But this is not a one-step problem like the ones we've been doing. This is actually a two-step problem. And it says, what is the mass of 4.61 times 10 to the 25 atoms of helium? So in this case, I don't have moles. And I can't go directly from atoms to mass. Now, if you were sneaky and smart, you could do this in one step. But in general, this is a two-step problem. In this case, I'm starting with atoms of helium. It's the only thing I've been given. So I'm going to start with 4.61 times 10 to the 25th atoms of helium. I know the relationship between mass and moles, but this time I have atoms. So the trick is I've got to get to moles first. And when I do that, I know that if I'm going to get rid of atoms of helium, I want to go to moles of helium. And I can do this because I know that 1 mole of anything is 6.022 times 10 to the 23 of that thing. When I solve this, it becomes 4.61 divided by 6.022, which is 0.76, let's say 766 times 10 to the 25 minus 10 to the 23, or 10 to the 2. This is not appropriate scientific notation. So it becomes 7.66 times 10 to the 1, or if you were to really solve it out, 76.6 moles of helium. And then I can take the next step and bring this over and say if I have 76.6 moles of helium, and I know that for 1 mole of helium, because remember we're getting rid of moles of helium, and we're going to turn it into grams of helium, I know that for 1 mole of helium, I have 4.00260 grams. I can figure out that 76.6 times 4.00260 is going to be 3 sig fig, approximately 307 grams of helium. So it's a multi-step problem. We had step 1 where we go from atoms to moles, and step 2 where we go from moles to grams. And we're going to talk about this later when we talk about the idea of mole island. But for right now, I just wanted to see that you could think through this challenge problem. And that's all I have on molar mass. So there is going to be a practice worksheet for you guys to do online. And I will go over the answers and put an answer key up when I am able.